around the world. Welcome to ACM AI's Beginner Track workshop series. And this is workshop number 2, where we're going to be talking about linear regression. So on the screen right now, you can see a link to the slides in case you want to follow along. The attendance code on the membership portal is Toy Story. And we've also linked the ACM Discord. And we have a channel specially dedicated to Beginner Track. So that's also a great tool if you want to use it. So in case you missed our last workshop, we're going to reintroduce ourselves really quick. My name is Sudhanshu Agrawal. My pronouns are he and him. I'm a second year computer science and mathematics double major, and I'm an officer here at ACM AI. I'm going to be teaching Beginner Track along with Jenson and Adithya. Jenson?
Hey everyone, my name is Jenson. I'm a second year CS major, and my pronouns are he and him.
Okay, and my name is Adithya. My pronouns are also he and him, and I'm also a second year CSE major. So yeah.
Awesome. So to quickly recap, Beginner Track is our introductory workshop series to machine learning. So we require absolutely no prior experience or experience with machine learning libraries. We're going to be talking about the fundamentals of machine learning, and we're going to talk about how the fundamental models like linear regression and logistic regression work. And we're also going to be talking about how we can implement them. We meet Tuesdays, 7 to 9 p.m. Pacific time at this very same link. So let's get started. And to get started, we're going to talk about some math. Now, the natural question is, well, why math? So machine learning is fundamentally a mathematical concept. There's a lot of statistics and probability involved. So having a background on these concepts is really helpful. Today, we're going to be talking about an algorithm called gradient descent, and that involves a little bit of calculus. But it's an extremely powerful yet simple algorithm that is used in pretty much every application you can think of. So if you have any questions, feel free to drop them in the chat. Don't forget to prefix it with @question. And also you can post it on the Discord after the workshop if you'd like. So we're going to get started by talking about derivatives. Now, derivatives, as we know, is the rate of change of a that if derivative is positive, as you can see in this part, the function is increasing. Symmetrically, if the derivative is negative, the function decreases. So now we're going to extend this idea to partial derivatives. And in the multivariable case, we have a function that depends not just on x, but on x and on y. That's why it's called a multivariable function, because there are two variables. If we want to find out how much f depends on x, we calculate this quantity known as the partial derivative. And to calculate it, we take y to be constant and calculate the derivative as we normally would. So let's explain this through an example. If we have a function f of x comma y that's equal to 2x plus 3y squared, let's say I want to calculate the partial with respect to x. The way I do that is by saying y is just some constant, right? It doesn't change at all. And what's the derivative of constant? Well, it's just 0. So that term pretty much just disappears. And then we can just take the derivative of 2x with respect to x, and we end up getting this 2. Similarly, if we want a derivative with respect to y, we say x is a constant. So x doesn't change, and when we take its derivative, it goes to 0. On the other hand, if we take the derivative of 3y squared, we end up getting this 6y term over here. So in this two variable case, we get two different partial derivatives. Similarly, in the end variable case, so suppose instead of just x and y, we had x1, x2, all the way up to xn. In that case, we'd have n different partial derivatives. And the way we calculate it is by saying, okay, for now, I want some xi to be the variable I care about. Let's say it's like x10 or something. So I'm going to keep x10 as a variable and keep every other variable constant. And by doing that, I can just take the derivative with respect to that particular x. So if you recall, an n-dimensional function has n different partial derivatives. What I'm going to do is I'm going to take all these partial derivatives and stick them in a vector. When I do that, I get the gradient. So that's literally just what the gradient is. It's a vector containing each of the partial derivatives. So this is the derivative with respect to x, with respect to y, and with respect to z. So this is a good point to take a quick pause. If anyone has any questions, please feel free to drop them in the chat or unmute yourself if you like as well. Okay, sounds good. So let's move on then. So just to make sure that we're all on the same page, we're going to do a really quick 1-minute poll. Just calculate the gradient of this function, right? And I'm going to launch the poll in 1 second. Okay. I keep trying to find a spot to put this. Okay, there you go. Going to give it another 5 seconds to make sure everyone votes. Okay, we can probably end it here. So I'm going to share the results with you guys. So that's really awesome. 95% of you got the right answer, which is A. So I noticed that a few of you chose B, and I can see the confusion here. So you got each of the components correct, but the thing to remember about the gradient is that you need to stick it in a vector. So you don't add it up, you just put it in a vector. Now, a small number of you chose C and D. So really quick, I'm going to explain why we got this answer. So the partial with respect to x is simply keeping y and z constant and taking the derivative with respect to x of this term. The derivative of this term is just 2x. Similarly, the derivative of this term is 2y, and this term is 2z. So I hope everyone is comfortable with that. Great. So now we're going to talk about this algorithm called gradient descent. And the objective of this algorithm is to minimize the value of a function. So if you look at this graphic over here, we start off at this point all the way up here. And our objective is to get to this minimum. And that's what gradient descent helps us do. We're going to start, as always, by talking about the single variable case. So if you look at this picture over here, this is a function y is equal to x squared. And our objective is to get to this minimum right here at 0. So suppose I just, for example, started off at this point. So somewhere along this right branch. And I would ask you, should I move left or should I move right? You'd say, well, you should probably move left. That would help us bring us closer to this minimum. Similarly, if I was on this branch and I said, should I move left or should I move right? You'd say, I'd probably move right. And that would help me bring me closer to this minimum. So let's think about why we thought about that. So suppose we didn't have this nice graph telling us exactly where the minimum is. Suppose I was just sitting at this point and that's all the information I have. Why did I think that I should move to the right? Well, I looked at where I am at this point, and I said that the function is sloping downwards, right? So if I were to move to the right, I'd end up slipping down the slope and moving towards the minimum. Similarly, over here, I said, if I'm standing over here, the function is sloping upwards. So if I want to get to the minimum, I need to go down the slope. So the slope is basically just the gradient that we just talked about. So we need to somehow move in the direction of the gradient. Let's go through this. So f of x is a function of one variable. F prime of x is the derivative, and it tells us whether the function increases or decreases. If f prime is positive, the function increases. What does that mean? It means that if x increases, f of x increases. But our objective is to decrease f of x, right? So we don't want this. Instead, we can say that if x decreases, f of x decreases. If we want to decrease f of x, we decrease x, and to decrease x, we just subtract something from x. I hope this makes sense, because suppose we have a number 5 and we subtract 1, we end up decreasing 5. So if we want to decrease something, we subtract some value from x. We're going to talk about what the sum value is in a bit. So similarly, if f prime of x is negative, if we want to decrease f, we increase the value of x. So it'll be a little more clear on the next slide where we summarize this. So to repeat, we want to minimize f of x. So if f prime is positive, we subtract something from x. And if f prime of x is negative, we add something to x. Okay, so now I've been pretty ambiguous about what this something is, right? So let's try and think about it a little bit. Notice that if f prime is positive, we subtract something. And if f prime is negative, we add something. So it seems to me that whatever this something is depends a lot on what f prime is. So this dependency tells me a lot. Maybe the something is just f prime of x itself. Why not just use this f prime of x as this something that we subtract or add? But we need to be a little careful. Notice that there's a system of opposites going on here. So we have positive, subtract, negative, add. So in a way, we want to do the opposite of what f prime of x tells us to do. So the way we handle that is by simply putting a negative. So we have our old x, we have f prime of x, and to do the opposite, we put this negative sign in front. So let's look at this equation through this example once more. If f prime was positive, it means we're on this branch. And if f prime is positive, this entire term becomes negative, and we end up subtracting something from x, which is exactly what we want to do, right? Because if we're here, we end up subtracting and going towards the minimum. Similarly, if f prime was positive, if f prime was negative, sorry, we are over here. So this entire term becomes positive because the negatives cancel out, and we end up increasing the value of x. And that's what we call an update, because this is the old value of x, and this is the new value of x. And we update x using the derivative of f. Now, this alpha that you see over here is just a constant that we choose. It's a constant used to scale how much we update the value of x, and it's called the learning rate. Now, the reason it's important is, say I was at this point, like really, really close to my solution, and x was like 0.1. But suppose f prime of x was 10,000 at this point. It's not in this case, of course, but for a different function, it could be, let's say, 10,000. Then if I subtract 10,000 from 0.1, I'll end up way overshooting my target, and I won't end up near my minimum. So this alpha helps us control how much we update x, and helps us reach this minimum more smoothly. So again, this is a good point to stop and take any questions. Does anyone have any questions? Okay, so we have a question here. How do we determine the value of alpha? Okay, that's a really good question. So we usually keep alpha pretty small. So a common range is, let's say, 10 to the negative 3. Because like I mentioned, if we have a gigantic gradient, but really tiny values of x, we want this update to be really small. And what we usually do is we take a value of this learning rate alpha, set it at the beginning of the optimization, and keep it fixed throughout. Now, there's a lot of other stuff we could do, like change alpha during the algorithm and whatnot, but that's not necessary for now. So I hope that answers your question. Let's see. How do you initially check the case that there is no minimum? Okay, so that's also a really nice question. And it's a little more involved, but it has to do with the fact that the functions we pick inherently are what we call convex. So they definitely have some kind of minimum. In some bad cases, we could have lots of minima. So we have like one local minima, then a global minima, maybe another couple of global local minima. And in that case, the optimization is a little more difficult. So we need to be a little more careful, and those involve some more advanced techniques. So do we use f prime of x simply because the sign of it is convenient? So the answer is yes, that's definitely a huge benefit, but it has to do with the fact that inherently the function, the derivative points in the direction of descent, right? So it naturally, by construction, is the slope. And if you want to slide down the slope, you naturally end up with a minimum. So not only is the sign of it important, but it's also the magnitude of it. So if you see at the point close to the minimum, the gradient is really small. So that means we're a lot closer. On the other hand, if we're up here, the derivative is really large. So that means we're quite far away. So the sign is important, but also the magnitude. And in total, f prime is just a really nice package to do this optimization. So another question, why do we continuously update by subtracting or adding the derivative instead of setting f prime of x is equal to 0? Okay, that's a good question. So in this example, we know exactly what f of x is, right? And therefore, we know what f prime of x is. But what often happens is that we don't actually know what the function that we're trying to optimize is. Or moreover, the function could be dependent on like 200 variables, and doing something like this analytically is practically impossible. So this is an iterative numerical method which helps us reach the minimum. Okay, awesome. Add question, why are we trying to minimize f of x? Okay, so that's a fantastic question. And the reason so the answer to that is going to come up in the next few slides. And essentially, we're going to frame our entire machine learning problem as this optimization. We're going to say that if I reach the minimum, my problem is solved. And so if we have an algorithm to reach the minimum, we can solve our problem. Okay, that's awesome. Let's see. If you have a derivative that varies wildly in magnitude, would you also have to update the value of your learning rate as you update x? So yes, absolutely. That's a really, really good comment. And you're absolutely right. So in a lot of cases, our function, like I mentioned, could be really messy. It could like oscillate like crazy, and we could end up with all sorts of local minima. So in that case, if we take these large fixed steps, we may end up overshooting our target like we did over here. So in that case, it definitely helps to possibly reduce the learning rate as we get closer to the minimum. And that's something called learning rate decay. It's a slightly more advanced concept, and we're not going to be covering it here, but it's definitely something to be kept in mind. Okay, so I'm going to let you guys ask any more questions in the chat, and let's start moving on. So just like before, we're going to extend this to the multivariable case. Now, if you remember, we had this gradient vector that we calculated. An important thing about this vector is that it points in the direction of steepest ascent. What that means is if I were to follow the gradient, if I was to walk along this vector, I would end up increasing the value of my function. But like before, we don't want to increase the value of the function. We want to decrease the value. So instead of going in the same direction, we go in the opposite direction. And that's what leads to this algorithm being called gradient descent. It means we go in the opposite direction as the gradient and thereby decrease the value of our function. So in formulae, the x that we were talking about is now a set, is an entire vector. So we have our x1 variable, x2 variable, all the way up to xn. Similarly, the gradient is also a vector. So for each of these variables, we have a partial derivative. The way we update our x is by simply vector subtraction. So we take this vector and we subtract this vector. And like before, we have this learning rate alpha, which helps us control how much we update our function. So that's gradient descent. It's a really, really cool algorithm, and it's extremely powerful. So I'm going to pause again for a couple of seconds. Does anyone have any questions about this case or anything else? Okay, so I have a question here. Is there a way to differentiate between a local and a global minimum? Okay, that's a really, really nice question. And the direct answer is no. So there's no actual way. So for a gradient, a local minimum is just the same as a global minimum, right? And the way we avoid falling into a local minimum is by actually changing this learning rate alpha. So we had a question before where someone mentioned, could we change this learning rate alpha? And that's exactly what we do. We try to escape this local minimum by kind of jumping out of it. And that's a more delicate process. And what we often try to do is we formulate our problem such that there are as few local minima as possible. So we try to make it as convex as possible. So there's another question. Can this algorithm work around a non-continuous derivative? Okay, I think I see what you mean. It's essentially you're asking, what if the function wasn't differentiable? And that's also a really nice question. So the way I'd explain that is the following. When we calculate these gradients when you're doing like neural networks or even with simple optimizations, the gradients are calculated through this process called automatic differentiation. And that's something way beyond the scope of this class. It's something I'm not completely comfortable with either. But this process essentially throws all of this math under the table and calculates the derivative in a really numerical manner, which also gives fantastic results. And it doesn't really care whether the function is differentiable or not. It's still going to tell you which way to move. So for example, if I had the function absolute value of x, right, which is this non-differentiable function, my automatic differentiation is just going to handle that. I'm not going to have any problems. So let's see, there's another question. What does f actually represent? So that's something we're going to be covering in the next few slides. As you'll find out, f actually represents what we call an error function. And our objective is to minimize the error, which is an awesome thing to do, right? What is the difference between the x vector and the gradient vector? So the x refers to all the inputs into our function. So let's say maybe a simple example would be x, y, z. Those are the three input variables. And the partial derivative, the gradient is the partial derivative with respect to each of those variables. So partial x, partial y, partial z. So let's see. Why is gradient the steepest ascent? I know how to calculate partial derivatives, but what do they represent? Okay, so that's also a really nice question, actually. So the reason the gradient is the steepest ascent is a slightly more involved concept, and it's something you're going to be covering in Math 32A if you're going to take that course. But to give you kind of an idea, right? What does the derivative represent? It represents that if I were to change x, how much would f increase? So in a way, each of these components is telling us what is the best way to increase f. So telling me if I just care about x, what is the best way I'll increase f? If I just care about y, what is the best way to increase f? So the best way to increase f overall is if we take all of these guys' opinions into account. We say, okay, I'm going to listen to x, I'm going to listen to y, and listen to z, and all of them at the same time. And that kind of gives you an idea as to why we care about this vector when talking about steepest descent. So another question, is alpha always positive? And the answer is yes. So like we mentioned in the previous, so if you see on this formula over here, we care a lot about what the sign of gradient of f is. And we don't want to mess with that at all. So we leave alpha to be positive so that it doesn't mess with that sign at all. Is the gradient along the function or perpendicular to it? So that's a really good question. And the answer is slightly involved. The gradient is, let me go to a previous slide. Okay, here you go. So the gradient, as you see here, is pointing in the direction in which you minimize the function. In a multivariable case, the gradient is going to be pointing at the normal to the surface. Okay, so now this is a slightly more involved concept. Please don't panic if you don't understand it. But if you have this surface over here, the gradient is going to be a vector which points outwards. So it's like, it's normal to the surface here. Actually, sorry, let me back up there really quick. The gradient is going to be pointing, my bad. The gradient is going to be pointing along the surface, but it's going to be perpendicular to this normal vector. So you see here, the slope is along the surface, whereas at this point, the normal vector is going to be perpendicular to it. So you have the gradient and you have a normal vector. So sorry about that mess up. And so, yeah, I think if there aren't any more questions, that is gradient descent. Feel free to keep asking questions in the chat, obviously. But now I'm going to hand it over to Adithya to talk about how we can use this concept. So Adithya?
Yeah, cool. Good stuff. So yeah, right now we're gonna like try to use a more real life example to kind of understand how all this like fits in together. So yeah, let's move on to the next slide. All right, cool. So an example problem, housing prices. Sudhanshu, you can just like kind of just show everything. It's fine.
Awesome.
All right, so let's take a look at one example. This is a pretty common example in introducing the concept of linear regression. So housing prices, we want to predict what the price of a house is. And obviously, in order to do that, we need to have like knowledge of certain aspects of the house. That's going to involve the square footage, how many rooms it has, the size of a backyard, a lot of different features. And conveniently, in linear regression, we call this information features. These are essentially the inputs that we would give to our model in order to estimate the price of the house, which has these certain features. So yeah, the price depends on these features, and the role of machine learning, the end goal of all of this is to essentially find a relationship between the price, which is what we're predicting, and the features of the house, which is what we have and which is what we give to a model. And that's how that's kind of how we're gonna like keep going with this. So next slide, please. All right, so take a look at these. Which one do you think is worth more? I think it's pretty obvious. Um, and again, we would talk about this with features, look at what are the features on the left, compare them to features on the right. And then you can kind of get a pretty good understanding of which house would be worth more. So yeah, just so then you can move on. Cool. So obviously, one of them was more expensive than the other, and that's kind of that rational thinking that you just committed to when you're comparing features, looking at both the houses, and then trying to like figure out a pattern. I could say you between both those houses, and that's how we want our machine learning model to think. Essentially, what we're trying to do is we're trying to simulate human rationale, basically. So yeah, here's some quick terms. Features, we just went through these, just properties of the object we're working with. In this case, it's houses, and the target or the label. So the target or label is the true value of what we're trying to predict. And again, in this case, that would be the price of the house. It is not, so don't get this confused with the prediction our model outputs at the end of the day. The prediction our model outputs is just a prediction. The target or the label is the true value of what we're trying to predict. So let's say for a given house with a given set of features, we would have both a target or a label, which is the true value of the price, and we would have a prediction, which is our model's prediction of the price. And as we'll see later later in this workshop, we would want to compare our prediction to what the target or the label is, and then we're gonna apply some gradient descent and all that fun stuff, and you're gonna see that pretty soon. So yeah, so can move on. All right, so this slide kind of gives you an understanding of how machine learning is a little distinct from traditional programming. So in the traditional programming, oh wait, I see a question. Let's see that. Would you say target when the output is continuous and a label is discrete? Yeah, I mean, so the true value of what we're trying to predict is always going to be let's see. Would you say target when the output is continuous and a label if it's discrete? Okay, so usually the output from the model and the label that we're trying to like match it against are usually of the same type. So they're both either going to be discrete or continuous, but either way, the true value of anything we're trying to predict is always going to be called the target or the label. That's why it's called a target. It's the value we want to get at the end of the day. When we put in a set of when we give our model some data, that is essentially what we want to get from our model. It's called a target because it is the expected value. So yeah, I hope that clears it up. Yeah, so back to this, traditional programming versus the machine learning approach. So in traditional programming, obviously, we have some inputs we want to give to a program that we would design. And then the program works on this data, and then eventually we get some results at the end of the day. But in the machine learning, it's flipped. So instead of inputting a program, we would input both data, which in this case are the features of the house, and we would put in results, which are the target or the price of the house. The machine learning approach essentially comes up with a program which initially doesn't work that well. When you give it some amount of data, the program that it figures out doesn't really work that well and doesn't give you the results you would expect for the given data you would provide. And that's where gradient descent kind of fits into all of this. It tries to work out the method, the way we want to change the program in order to eventually reach a point where the data we provide gives results or predictions that match the target variables for the data. So that's how traditional programming machine learning is distinct. we're going to see how that works in a little bit more detail in the next few slides. So Sudhanshu, you can move forward. Yeah. So machine learning, again, if you remember how we kind of defined what exactly AI was, it's artificial intelligence. We are trying to simulate how humans think, and humans love to think in patterns. We notice patterns, and we try to we kind of try to like figure out patterns between between all the things that we experience, and kind of like make our prediction based on that. That's essentially what we're trying to do here as well. We have some features, right? These are like the aspects of the house, number of bedrooms, square footage, all that fun stuff. And we have targets, which is the actual price of the house. And what our model is trying to do here is it's trying to find a trend between all this huge amount of data that we provide, and based on those trends and patterns that it recognizes, that's kind of how it's going to make its predictions on data that we feed it that it's never seen before. And that's why ML is so useful. Okay, let's move on. Right. So the machine learning pipeline, obviously it's a little bit more complicated, but we try to make it as simple as possible and break it down into 5 stages. So in beginner track, we're mostly going to be looking at training and testing with a little bit of pre-processing involved. And I'll still go through all of the stages real quick. So input data is when we kind of try to collect all this data that we would want. It's essentially it's a data collection phase. The more data we have, obviously, it's always going to be better. In the pre-processing stage, that's where we kind of try to modify the data a bit by removing like outliers that would really throw off our the final sort of algorithm that we would want to develop, or scaling the data and all that fun stuff. And we will take a look at that. We're going to take a look at some data analytics techniques in one of the next few workshops. Yeah, so training, that's the part where all the magic happens. That's the gradient descent part, where we're trying to kind of figure out how to change our function so that it eventually it predicts values that we would expect. Again, and testing, it's going to use some data that our model has never seen before to ensure that our model is accurate. And there's always usually some amount of cyclical behavior between testing and training. You would train, then you would test, and then if you realize, oh, our model isn't that good, we go back to training, and it's pretty much like a loop. And interpretation, that's where we kind of like look at the model we've chosen. Do we think a different model would work better, or do we want to introduce more features so that we could get a more accurate model? So yeah, this is the general ML pipeline. Obviously, it's very simplified, but for the time being, this is pretty much all you would need to know. So, Sudhanshu, you can move on. All right, cool. Representing our data. So when you would begin sort of like when you receive the data and you would try to like look at it, kind of like try to clean it up a bit, as we saw in the pre-processing stage. This is kind of how it would be presented to you. It looks very much like a spreadsheet, because that's essentially what spreadsheets do. They're like a good way to represent data. So real quick, when you see each row in this sort of data representation, each row is essentially contains information about one single house. In this case, a house, but in a more general case, it would be one single point. So you can think of like bedroom, square feet, neighborhood as different variables, right? And these different variables somehow combine together to influence the price which is what we're trying to find. So each column is a feature, like I just mentioned, and the target, as we mentioned before, is the true value of what we're trying to predict. So let's say we would give our model that the number of bedrooms we have is 2, the square footage is 800, and if the town is hipsterton, we would expect our model to throw out 300,000. Once again, don't confuse the target with the prediction. This 300,000 is what we would expect. Our model might initially give out some random values like -3 billion or whatever. That's the whole point of machine learning and gradient descent. We want to change our function that output this horrible value and slowly change it over multiple iterations, as we saw in gradient descent, to eventually get to a point where a function can accurately spit out some results that matches our target values. So yeah, before I move on, are there any questions? I can kind of answer them right now. Okay, so I think I got a question. I'm not sure, but I think it says, are the features variables, x, y, and then ... n number of features? Let's see, features, variables. Well, yeah, so if you could, okay, so let's think about like a general sort of like a 3D, a three-dimensional graph. You have x, y, and z, and usually you would have x and y combined in some way to represent z. So that's it's pretty analogous to what we see here, where you can look at these features like bedroom, square footage, neighborhood. You can think of these as different variables. And these variables are usually denoted as x1, x2, x3, all the way until xn. If in the case you have n features, these n features could be 10 or it could be 200. It kind of depends. And all of these variables kind of combine in some way, as we're going to see in a function, to give what y is, and y in this case is the target, and that's kind of what we're trying to simulate with the machine learning model that we're trying to make, linear regression in this case. Yeah, so then you can move on. All right, cool. So yeah, all of this, at the end of the day, all of this is to figure out a function. What is a function? Pretty simple. It takes in some input values, gives us an output, and this function essentially is going to give us the desired price, and we call this function the hypothesis, and it's, as you can see, it's denoted by y hat. So again, it's like as I mentioned before, it's important to draw this distinction between what our model gives us and what the true value of the true value of our price is. And that's why we called, if you remember correctly, in the previous slide, we called our target list y, and our hypothesis in this case is y hat. So again, we're going to see how this works together in the next few slides to eventually apply something called an error function or a loss function to figure out a way to apply gradient descent. We're going to see that shortly. Yeah, so then we move on. All right. So model, I've been saying model a lot. So what exactly is model or a model? So a good way of thinking about what exactly a model is, just think of it as the techniques a machine would use to answer a problem in a particular context. There are various different models we could use. In this case, in this workshop, we're focusing on linear regression. But as you can see over the next few workshops that we have, there are a whole host of different models. We're talking logistic regression, KNN. We're going to see a lot of different models in this workshop and in future workshops. So yeah, Sudhanshu, can you move on? Right. So for housing prices, one would assume that you could, there's a question, is a model like a formula? Not exactly. So you, if you remember, we talked about the hypothesis function. That's kind of the, you could, I wouldn't use formula. It's like the function that we would use to provide our predictions. A model is more like the way a computer chooses to approach a particular issue. It's about how a computer chooses to interpret an issue based on the context we provide. So in this case, for example, we're trying to predict prices, and prices are a continuous would give us like a continuous output. The function we would expect is to the function the function would essentially give us a continuous output. That's what we would expect. In different situations, we might expect more discrete outputs, and in different contexts, we're gonna be dealing with different situations, and that's exactly what a model is. Yeah, so in general, it's what the solution would look like precisely. So again, in this situation, we're looking at an output that's more continuous. In different situations, we would want more discrete outputs. And there's gonna be a whole host of different models. And if you can take the time to look up different machine learning models, you'll see a whole host of different models, and you can also see a description of when each model is to be used. It depends on different factors. We're talking about like what the data is, what our output is. Again, definitely look that up. There's a lot of different models. We're gonna be covering 3 in beginner track, but trust me, there's a lot more. Yeah. So yeah, in this case, as it says, a linear model is a good fit, hence linear regression. And the reason for that is we expect each sort of feature to either be to be proportional to the price, you could say. Like if one feature's value increases, we expect the price to either increase or decrease. So in either case, it's going to be proportional, and that's essentially an assumption. Obviously, in different situations, in different contexts, that's going to be different, and hence we would use a different model. But in this case, a linear model is a good fit. So yeah. All right, so I see another question. Do different models actually produce different results? Yeah, so that is a fair point. Yeah. So again, different models, like as I mentioned before, like a really good way to think about this in 2 different ways is you could have a linear model, which is what we kind of see on the screen right now. And in the next workshop, we're going to actually see something called a logistic regression, which is going to kind of convert our continuous output and kind of like try to squeeze them apart and put them in 2 like discrete categories. So we're going to see that. But yeah, thinking about models producing different results, I would say that is a good way to think about it. So yeah, Sudhanshu, you can move on. Right. So we have a whole bunch of different letters in this function. What exactly are they? So yeah, um, so W1 through Wn, these are known as weights. And we have another constant called B, which is the bias. And they're known as learnable parameters of our model because these sort of variables, not variables, but these values um, changes during the machine learning process where we apply gradient descent. Um, and don't worry, we keep saying gradient descent like it's a big deal, but you will eventually see like how it works and all that fun stuff. But yeah, they're called learnable because throughout the process, the training process, these weights and this bias are slowly shifted around um, ever so slightly based on what our results are and how these results or these predictions from our model compare to the true values or the target. So these weights and this bias is slowly shifted here and there until our function kind of um, gives us the predictions that we wanted to give. All right, so question. So there is a different weight for each feature. Exactly, precisely. So x1 through xn, these are the different features of our problem here, the house price problem. And each one of these features will be assigned a different weight. And we're gonna see why exactly that is. Most and I guess I'll talk about it right now. Yeah, good question. Weights can be negative. Absolutely. Let's say, for example, you have one like feature, which is let's say how old the house is, and we have another feature like the number of bedrooms it has, for example. You would assume um, that the weight associated with um, the feature that represents how old the house is to be negative because when we think about um, time versus the price of a house, in a very general case, you would expect the price to decrease as the house the age of the house increases. Um, in contrast, when the number of bedrooms of a house increases, you would expect the price to increase as well. So you can kind of understand why what these weights exactly are. These weights are the importance we associate with each feature. Um, so the most important features, the features that really influence what the price of the house is, that's going to be a very positive weight. And the features that reduce the price of the house the most, those weights are going to be the weights corresponding to those features are going to be more negative, so to speak. Let's see, question. How do we know if it's possible to model our relation using a linear function? Will a linear function always be able to approximate a relation? No, absolutely not. We're taking a very general, or I would say a better term to use is we're making an assumption here, and that's kind of part of the process. When any situation where you're trying to model a real world scenario, there's always going to be a certain set of assumptions you're gonna have to make. We're kind of building off of these assumptions. We're kind of building off the fact that building off the assumption that um, prices in the house prices in this case are like directly proportional to each of the features. But again, that's not always true, and we're gonna see that over the course of these workshops. Let's see. All right, what's the difference between statistics and machine learning? Okay. Um, let's see. I guess it's a pretty general question. It's statistics and machine learning are definitely deeply intertwined. But machine learning, again, is the process of finding an algorithm that simulates human thinking. That's kind of our end goal here. When we think of predicting the prices of houses, how did we used to do that before the advent of computers? We were doing it with our brains. We kind of see all the features of the house, we do a little bit of math, and we get a kind of come up with a price. In machine learning, all we're doing is making the computer do the same thing. And yeah, statistics is just dealing with data, looking at prediction, looking at patterns in that data. So again, definitely intertwined, but distinct as well. Yeah, so Sudhanshu, you can move on. All right, quick poll. A little bit of interaction. Why not? So here's a question. It was too long to fit on the poll question, which is why you probably won't see it on the poll. But so this is a situation. We're assuming another assumption that the price of the house depends on 4 features: the number of rooms it has, how long ago it was constructed, the crime rate in the neighborhood it is in, and the distance of the house from the closest hospital. And let's also say that the neighborhood crime rate and the number of rooms affect the house price the most. Which feature would have the most negative weight? Sudhanshu, you can go ahead and start the poll. All right, we'll give it a few more seconds. All right, cool. So about 90% of y'all here voted. So yeah, most of you got it for sure. Neighborhood crime rate. But like we're also seeing some people choose how, like, the age, how long ago since construction, number of rooms, and distance to closest hospital. So it's important to look at the wording of the question. So we're saying that, okay, the house's price depends on 4 of its features. 2 of these features influence the price of the house the most. And then which feature has the most negative weight. So when we see negative, obviously the first thing we have to think about is if the weight is negative, that means the house's price is negatively correlated with the feature that we're looking at. And obviously in this case, it's going to be the crime rate and how long ago it was constructed, based on like logic essentially. And then when we say the most negative weight, that means the magnitude of the weight needs to be the highest possible, because the weights that influence the price of the house the most will have the highest magnitude. And in this case, obviously, it's going to be the neighborhood crime rate, because number one, the neighborhood crime rate is going to be negatively correlated with the house's price. And it's the most negative weight because we mentioned in the question that it is one of the features that affects the price of the house the most. So yeah, let's move on. All right, cool. So the parameters to the hypothesis function that we have. So an input x, just the n-dimensional vector for the n features in the example. Remember, the input x contains all the features for one house. So n features, one house. So in the grand scheme of things, if we have, let's say, 500 or 600 houses in our data set, then we would have 600 distinct vectors. The weight W is also an n-dimensional vector, and obviously it has to be n-dimensional because, as we discussed before, each weight needs to correspond to a particular feature. So W1 corresponds to X1, W2 corresponds to X2, and so on. So they need to be they need to have the same dimension, like essentially. And the bias is a real number. It's mostly just used to translate our model so that it can fit our predictions a bit more. We'll definitely talk about that in the future. So yeah, let's move on. All right. So how do we represent our model? So obviously the long format is going to be y hat x equals all those terms. Another way of doing that is using the dot product. And if you are not familiar with the dot product, it's basically an operation on two vectors of the same dimensions that multiply the corresponding components of those vectors and sum them all up. So you can think of them as a sum of products. And moving on, next one. And if you look at and obviously, since in machine learning, most like computations are very matrix heavy. So there's always, I guess you would say, a preference to use matrix notation in as many cases as possible. And we're gonna see that. I guess you're going to see it when you begin taking advanced track and dealing with neural networks. You're going to have pretty chunky matrices to deal with. But for the time being, we're looking at the transpose of the weight, W matrix, the weight matrix, multiplied by the X matrix. So for the individuals who are not too familiar with this sort of matrix multiplication, I'll just quickly kind of jot it down and show you how it works. By the way, Sudhanshu, I'm sharing my screen, just a heads up. All right. So if you remember right, we the first situation was we have W dot X plus B. That's the dot product. We can assume W. Let's just assume W to be a vector containing 3 different weights, and obviously X also needs to be the same. X1, X2, X3. So when we apply this this dot product, we are going to essentially multiply each of the corresponding components. So that's going to be W1, X1 plus W2, X2 plus W3, X3 plus B. And that's essentially the format of our hypothesis function. That's the end goal that we're trying to get to here. The other sort of representation we saw was the transpose, and this transpose is, as you can see here, WT kind of hanging at the top. That's known as the transpose of a matrix, and since W is represented like this, taking the transpose of it kind of just like flips it. So you're going to get W1, W2, W3. So it kind of just flips it. That's just a nice way to think about it. And when it comes to the multiplication aspect, we're gonna. So this is essentially going to become W1, W2, W3 into, and this X stays the same. So it's X1, X2, X3. And obviously, I'm not going to get too deep into what exactly matrix multiplication is when you have like let's say n by m sort of matrices. That's going to be a little bit more complicated. But in this case, all we're going to be doing is we're taking W1, multiplying it with X1, W2 multiplying by X2, W3 multiplying it by X3, adding them all up together. So you're going to get W1 X1 plus W2 X2 plus W3 X3 plus B. That's just to kind of to give you an understanding of how exactly the transpose matrix and how you can kind of multiply these matrices together. It might seem a little weird at the moment to kind of do it like this. You could just say, oh, you could just use the dot product, right? Yeah, for sure. But as you'll see in the future, once you begin taking a look at neural networks, you're going to see these weight matrices like balloon up into these massive matrices with both columns and rows, and there's a reason we use these sort of like transpose matrices to represent our weights, and you're definitely going to see how that works out when you begin taking a look at advanced track. Yeah, Sudhanshu, you can take over again. All right, great. So yeah, I think that's about it from me. So Jenson is going to take over. He's going to go over the loss function, what that means, and how that's important, how that's integral for us to like use the whole gradient descent thing. So yeah.
All right. Can you guys see my screen now?
Yep.
All right, cool. So before our machine learning model can properly learn, we first have to talk about something called the loss function. So the loss function is sometimes being referred to as the cost function as well. So just keep that in mind. So what the loss function essentially does is that it measures the error in your predictions compared to the target values that you provide. So there are actually like many choices of loss function out there, but for linear regression, the mean square error seems to be a pretty good candidate. So that's what we're gonna go with for beginner track. All right, so let's walk through some of the terminologies here. So Y is the actual target value, which is right here. Y hat is the predicted value, which is denoted right here. And the index I is just the ith training sample in our data set. So as the name of the loss function suggests, we're taking the difference between our target value and the predicted value. And then we're squaring that difference to make sure that it's always going to be positive. And then we're just going to take the average of this value over the entire training data set. So hence the summation notation and the 1 over m. All right, cool. So the loss function can actually also be thought as a function of weights and biases. So this actually like was pretty mind-blowing to me at first, but if you think deeper about it, the loss function is basically just a function of your predictions, and your predictions are functions of all the weights and biases of your model. So it's not too difficult to see why the loss function is also a function of the weights and bias of your model. You can actually verify this by plugging y hat, which is our prediction, into our loss function as input. If you do that, you can rewrite your loss function just in terms of all the weights and bias, as well as your target value, which is y, and your features, which is x. All right, so I just like dumped a lot of information towards you guys. So if you guys have any questions about loss function, now would be a good time to ask. Also, feel free to unmute yourself. All right. So before I move on, I just want to make sure that we're on the same page. So we're gonna do a real quick poll on loss function. So just give me a second. All right, the poll is launched. All right, I'm gonna wait for 10 more seconds. All right, so most of you guys picked the first choice, which is error of the predictions that your model makes compared to the true value, which is the right answer. So good job. Some of you actually picked the third choice, which is the weights of your model. So that's not entirely accurate because like, even though the weights, the loss function is a function of your weights, it is not like measuring like what those weights are, it is measuring like the error. All right, so let's move on. All right, so like I just mentioned, our loss is a function of all the weights and biases of your model. And so when our machine learning model learns, so what goes on under the hood is that like is updating its weights and biases. And so if the loss function outputs a really small value, then our model is considered to be accurate. And similarly, if our loss function outputs a really big value, then our model is really lousy. So now we have reframed our problem to just finding the combination of weights and biases for which the loss is minimized. So how do we do that? Just type in chat real quick, I guess. All right. So you guys guessed this through gradient descent. So here's a visual for it in case you need a refresher real quick. All right, so we're gonna minimize our loss through gradient descent by taking the gradients of our loss function. So basically we're just taking the vector, our gradients, which is a vector of all the partial derivative of our loss with respect to each weight and bias, as denoted by these two formulas here. So the math behind like what needed to derive these gradients is actually pretty complicated. So I'm not gonna do it on the spot, but like if you're curious, like I've linked the full derivation of the gradients like in the slides. So if you're interested, like you can definitely like check it out. I think it'll be pretty cool. So now that we have our gradients, we can update our weights and biases through these two equations here. So yeah, now that we have introduced the idea of a loss function, I feel like now would be a good time to like do a demo on how gradient descent works on a loss function. Wait, hold on. All right. So we're just gonna work in 2 dimensions here, just so like it's easier to visualize. So we're picking our loss function as x squared plus x, which is this parabola. And then our starting point is at x equals 5, and we're gonna use 0.25 as our learning rate. So as you can see, it takes about 10 iterations for us to reach our minimum. But what if we change this learning rate to something like 0.02. As you can see, this takes a lot longer now because our learning rate is like really small. So now you're wondering like, what happens if we try a learning rate that's like pretty big, right? So let's try 0.9. So as you can see, we're consistently overshooting now. So this actually takes longer than our default learning rate, which is 0.25. But so yeah, so a larger learning rate is not always gonna reach the minimum faster. So like if I increase the learning rate by even more to like 1.1, yeah, this is actually not gonna converge at all. As you can see, our loss is actually diverging towards infinity. I'm just gonna try to zoom out. All right, yeah. Yeah, we're just diverging towards infinity, so that's not at all what we want. All right, let's go back to the slides. All right, cool. So like in the example that I just did, the learning rate is a constant, but obviously this is not the case like in practice. So one approach is to start off a pretty big learning rate and then just decrease it over the course of training, just so like we can converge towards the minimum like faster. All right, so I see a few questions. Let's see. Is there a specific way to determine a reasonable learning rate, or is it just guess and check? So like Sudhanshu mentioned, there are definitely like theories behind like picking the optimal learning rate, but like, you know, like for beginner track, it'll be enough to just like do it by trial and error. Like if your loss is diverging towards infinity, then you need to pick a smaller learning rate. If it's taking like too long for your loss to converge towards the minimum, then you need a larger learning rate. Okay, I think that's all the questions that I see. All right, so what we just went through, like what linear regression does is it basically just finds the optimal hypothesis, which can be thought as like finding the best fit curve. So the best fit curve ensures like minimum loss. And hopefully like most of you have some kind of experience dealing with this in 2 dimensions. But if not, you can refer to this GIF here. So this is basically how linear regression with one feature works. It's pretty easy to visualize it. And actually, like, if you don't quite get it just yet, don't worry, because we'll implement this in one of our guided projects later in the quarter. All right, so after we learn our weights, the training part of our machine learning model is done. So we have to test our model. So we'll first select some of the data points we have. Well, that just to specify, that is completely different from our training data set. Because if it's not different, then it will be counterproductive. Sorry about that. We then have to feed the input features of those data points into our model. And obviously, we're going to keep aside the true Y values because we're testing our model, not training it. And then our model generates predictions using the features, and then we compare the predictions to the true Y values to compute the loss using our mean square error. All right, there's actually a lot going on in the chat. Okay. Yeah, I'm assuming all the questions in the chat is resolved. So the loss tells us how well our model has performed. So just to reiterate, a lower loss means like the model is performing like better and vice versa. All right, so what we just did in this workshop is one of our supervised learning models, which is linear regression. So basically what we did was we told our model what the right answer was, and then our model like did its thing. But there are actually like other types of supervised learning, like classification, which we're gonna go for like in the next workshop. And we just did regression. All right, here are some like example of like classifications or regressions. Like feel free to think about these like after the workshop, but we're not gonna spend too much time on them. So there you have it. So again, what we did was a form of supervised learning. So our beginner track is going to be focusing mostly on supervised learning. And the next topic to learn is logistic regression, where we'll be classifying objects into like different classes instead of predicting like values. All right, so that's basically it. Thank you for coming. Please fill out our feedback form here because your feedback is very helpful to us. And yeah, feel free to check out our Facebook group and our GitHub, and we'll see you guys next week. Feel free to stick around if you have any questions, and we'll try to answer them.
Hey, thank you.
Yep, no problem.
You can probably stop the recording.
Okay, yeah, sure. I'm gonna stop screen sharing.